Kinematics. This is the next topic that we've got. Now, first of all, in kinematics, you need to know some basic terminologies. There are 6 different quantities that we'll be dealing with here: distance, speed, time, displacement, velocity, and acceleration. Some of these are scalar quantities, the others are vector quantities. Scalar quantities are those quantities that only have magnitude, they don't have any direction, and they're always positive. Distance, speed, time, they always will have positive values. Displacement, velocity, and acceleration, these are vector quantities. So they can sometimes be positive, they can sometimes be negative. These are vector quantities. Now, the corresponding quantity for distance is displacement in vectors. The corresponding vector quantity for speed is velocity. And we have time and acceleration. These are different from each other. Let's understand them. Distance is fairly straightforward. Distance between 2 points, the length between 2 points. I'm sure all of you understand this. Time is time. What about speed? First of all, speed is defined as distance over time, but it's not just any speed, it's the average speed. Average speed is given by total distance over total time. So if somebody goes from one point to another point and distance is this, time is this, you say the average speed is given by 16.7. That's distance over time. It's average speed. You cannot say that at any particular point the speed was 16.7. It's the overall average. So that's the speed formula. It's the rate of change of distance. What about displacement? Displacement is the shortest distance from a starting point. So let's say you've got an object that starts from A and it goes to the point B and then it comes back to C after that. Now, what's the distance traveled? Now, these terminologies are very important. Distance traveled. Distance traveled is 250 in one direction, 150 in the other direction, and distance plus minus does not matter. So we say it's 250 plus 150. That's 400 meters. That's the total distance that is traveled. If they ask you for displacement in this, what's the displacement? Displacement is shortest distance from the starting point. Now, in this case, since displacement is a vector quantity, we consider the right side positive. If the right side is positive, this is the starting point, and you reach the point C. This distance is 100 meters. You would say displacement is 100 meters towards the right side, or you can say it's plus 100 meters. If they ask you for distance AC, what about that? Distance AC. This is different from distance traveled. Distance traveled is this whole thing, 250 plus 150. That will be 250 plus 150, that's 400. But distance AC, that basically means distance between the points A and C. And that's the same as displacement. That in this case is going to be 100 meters as well. That is not 400 meters. So when they say distance traveled, you add these two. When they say just distance between 2 points, that is just going to be the same as displacement value. But since they're talking about distance here, it's only going to have magnitude and no direction, but the value is going to be 100. Okay, so that's the idea of displacement and distance. If you have something like this, it starts from A and it goes towards right 75 meters, and then it comes back by 100 meters. If you consider the right side positive, you can say the displacement in this case is minus 25 meters, because we're considering the right side positive. From the starting point, the displacement is towards the left side. So that's negative 25. That's the value for displacement that we've got. Okay. Next we've got velocity. Velocity is defined as displacement over time. Again, that's the formula just for the average velocity. Average velocity is given by the total displacement over total time. Now, if you have an object that goes like this from point A to point B and then comes back from point B to point C, the same example as before, if you had to find the average velocity in this, you would say that's the total displacement, that is 100, divided by the total time, that's 25. The average velocity turns out to be 4 meters per second. Average speed, on the other hand, that would be 16 meters per second. These are going to be different values. Okay, they're not going to be the same values. If you want to find velocity and speed at a particular point, for example, let's say you've got a point X here, you've got another point Y here, and we know the velocity, the speed at this point X is 30 meters per second, and the speed at the other point Y is 7 meters per second. The speeds are going to be 13 and 7. What about velocity? Velocity will have the same magnitude as well. That's going to be 30 meters per second for the point X, if you consider the right side positive. But it's going to be 7 meters per second at the point y, because minus 7 meters per second at the point y, because you're going in the left direction. We consider the right direction positive. The velocity value is going to be negative in this case. It's minus 7. But notice the magnitudes remain the same. They're 13 and 7, 13 and 7 for both speed and velocity. So at a particular instant, the values of velocity and speed, they're going to be the same at a particular instant. However, their average values, they may be different when the object is changing direction. When the object is changing direction, what happens is the distance and displacement are different values. For example, in this case, distance is 400, displacement is 100. So their average velocity and average speed, they're also going to turn out to be different. But instantaneous speed and instantaneous velocity, which were the speeds and velocities at these particular points, they will always have the same magnitudes. Only the plus minus would be different, because velocity can sometimes be positive and can sometimes be negative. Average speed and average velocity, they're always, they can sometimes be different. Instantaneous velocity and instantaneous speed, they're always going to be the same magnitudes. Okay. What about acceleration? Acceleration is defined like this. It's final velocity minus initial velocity, v minus u over t. This is also the formula just for the average acceleration, or when acceleration is constant. If you know acceleration is constant, or you're looking for the average acceleration, you can use this formula, v minus u over time. For example, if you have an object like this, it starts from point A, goes to point B, its velocity increases from 2 to 5. The change in velocity is 5 minus 2 divided by the time taken. That's 15, and that turns out to be 0.2 meters per second square. So acceleration is the rate of change of velocity, the rate at which velocity changes. So in this case, 0.2 meters per second square. What does that mean? In every second, on average, the velocity is increasing by 0.2 meters per second. If it was a negative value, for example, in this case, it starts from 15 meters per second, ends at 5 meters per second, the acceleration turns out to be negative 0.667. That means every second on average, what's happening is the velocity is decreasing by this magnitude, and we say deceleration is 0.667. So negative acceleration, we can write that as deceleration as well. Okay. Now, this is now the most important part from this discussion, and then we move on to the more relevant part for the questions. This is some basics. These are some basics that you needed to understand before we could actually go to the part on which you get problems. Let's say we have a point here, that's point O, and an object goes from O to A, and then it goes from A to B. It goes like this. Now, think about this part of the journey from O to A. When the object is, for example, at this particular point here, what can we say about the velocity value, and what can you say about the displacement value? Considering that the right side is positive. If the right side is positive, what can we say about the displacement value here? The displacement is going to be positive. What can I say about the velocity value? Velocity is also going to be positive. Why are they both positive? Displacement is the position of the particle from its starting point. From the starting point, the particle is on the right side, so displacement is positive. Velocity is also positive, because that's the rate of change of displacement. Displacement is increasing here, so velocity is also positive. The particle is going in the positive direction, the velocity value is going to be positive. When the particle is here on its return journey, when it's going towards the left side here, what about the displacement and velocity values at this point? At this point now, at this particular, sorry, where did that go? At this particular point, the displacement value is still going to be positive. Even though the particle is going towards the left side, the displacement value is still going to be positive, because what does displacement measure? Displacement tells you the current position of the particle with respect to the starting point. The starting point was this. The particle is here. From the starting point, it's on the right side, and the right side is positive. So displacement at this point is also positive. Velocity, however, at this point is going to be negative because the particle is moving towards the left side. If it's moving towards the left side, what's happening to displacement? Displacement is decreasing. You're getting closer to the starting point. Displacement is decreasing. Because of that, the rate of change of displacement, that's negative, velocity is negative. So displacement being positive, that does not mean that the particle is moving towards the right side necessarily. It just tells you that currently the particle is on the right of the starting point. That's all that it means. So this understanding is very important. Understanding the positive and negative values of displacement and velocity. Displacement is positive. If the displacement value is positive, what that means is the current position of the object is to the right of the starting point. So in both of these cases, at this point and at this point, the current position of the particle was to the right side. It was on the positive side. It's not a number line. It's not a number line. It's an object moving in the right direction first and then going to the left side. This is the starting point. O is the starting point. It's not zero. It's the starting point O. Okay, it's moving to the right and then going towards left. Now, while it was going towards the right side, at this point, displacement is positive because the object is to the right of the starting point. At the lower point here as well, displacement is positive because it's to the right of the starting point. It does not matter if it's moving towards left or it's moving towards right at that instant. Only the current position matters. If the current position is on the positive side, the value of displacement is positive. And a negative value of displacement means that the current position of the particle is to the left of the starting point, assuming that the right side is positive. So in this case, for instance, if the particle was here at this point you would say the displacement is negative because the particle is to the left of the starting point, that it's negative displacement. What about velocity? Velocity, its positive and negative values tell you whether the object is moving towards the positive side or moving towards the right side. So direction of motion is only given by velocity. Displacement cannot give you direction of motion because in this case, you saw that direction of motion was towards left side, but displacement was still positive. Okay. Velocity, however, is going to tell you the direction of motion. A positive velocity means that the object is moving towards the right. A negative velocity means that the object is moving towards the left side. So you can see in this part, velocity is positive, and in this part, velocity is negative. And what is the positive and negative value of acceleration going to tell you? That just tells you whether velocity is increasing or decreasing. If the velocity is increasing, acceleration is positive. If the velocity is decreasing, acceleration is negative. So acceleration is positive and negative values. They tell you whether the velocity is increasing or the velocity is decreasing. At this point, for instance, for displacement and velocity, displacement is negative, velocity is also negative. If the particle was to go in this direction afterwards, maybe it changes direction again, it goes like this. At this point, displacement would be negative, but velocity would be positive because the particle is moving towards the right side now. Okay, so displacement just tells you about the current position, and velocity tells you about the direction of motion. So only velocity can tell us the direction of motion. If the velocity value is positive, that means the object is moving towards the positive side. If the velocity value is negative, that means the object is moving towards the negative direction. All right. Okay, now let's come to the actual concepts in kinematics after this. These are some basics that we wanted to understand. First of all, these basic terminologies. Let's look at this now. So first of all, there are three different parts of kinematics. One part is where you have to use constant acceleration formulas. Another part where you have to use differentiation and integration. You will have some equations given, and using those equations, you have to find some values using differentiation and integration. We call that variable acceleration or kinematics using differentiation and integration. That's the second part. And the third part is graphs of kinematics. There are three different sections that we've got here. First of all, we've got these constant acceleration formulas. These are constant acceleration formulas. There are 5 of these equations. 4 are given in the formula sheet. The first 4, they're all given in the formula sheet. You could remember another one as well that sometimes make things slightly more efficient, although you can do everything with these 4 as well, and you can do everything using this as well. That's also fine. For the last equation, if you want to remember that, since this is already given, you can make this last one by replacing u with v, as in that's just a way to remember. That's how I tend to remember this. In this equation, replace u with v and flip the sign. Replace u with v and flip that sign. Now, there's a background to these equations, where they come from. That's not for a revision class. I'll skip that. So we have these 5 equations. S represents displacement, U represents initial velocity, V represents final velocity, A represents acceleration, T represents time. When can you use these equations? Only when acceleration is constant. These are called constant acceleration formulas, or you can say equations of motion. But remember, they're only going to be used when acceleration is constant. If acceleration is not constant, you cannot use this. This is the condition for using these formulas. Acceleration has to be constant. Yeah, so however you want to remember this, this is how they're given in the formula sheet. This is how they're given in the formula sheet. You can rearrange them as well. For example, this has, sometimes people write it as v² minus u² equals to as. That's also fine. However, you can remember this. That's okay. They're also given in the formula sheet. Now, these are called constant acceleration formulas. We will be using these formulas to find any missing quantities. For example, in the first equation, if you knew value of u, v, and t, you could find displacement. If you knew the values of perhaps v, u, and s, you could find time from that. So you would have 3 things given and the 4th thing missing. You can find that missing thing using these equations. For example, you have this particle that is going from point A to point B. You've got the initial velocity, that's 2, final velocity, that's 10. Time taken for this is 50 seconds. It takes 50 seconds to go from that initial point to the final point. Now, we want to find the displacement from A to B, and we want to find the acceleration from A to B. How do you do that? Displacement is S. Which equation connects these 4 things? S, T, U, and V. These are the equations that are given in the formula sheet like this. That's the only thing that's given in the formula sheet for mechanics. Everything else you have to memorize. All the other formulas, apart from these 4 equations, you have to memorize. You have these 4 equations given. You can see which connects S, T, U, and V. That's this equation. So you just use that equation, find the value of S from that. For this, you have acceleration that you have to find out. Again, which equation connects A, V, U, and T. You can see which one that is. That's V equals U plus AT. You use that, and that gives you the value for acceleration. Now, sometimes it's more complicated than that. For example, you have the situation in which you are given that a car is traveling at constant acceleration, and it passes through 2 points A, B, passes through 3 points A, B, and C. The time taken to go from A to B and from B to C is 5 seconds. This is 5 seconds. This is also 5 seconds. The speed of the car at A is given, that's u meter per second. And the distances are given 55 and 65. We need to find the values of A and U. Now, there are 2 parts of this journey, AB part and BC part. Now, one way to break this journey down could be like this. You could say A to B part. What do we know about this part of the journey? We know the value for time, that t is equal to 5 here. We know the displacement, that's 55. For the second part of this journey, we know the time is equal to 5 and displacement is 65. Now, in the remaining things, when you have multiple parts of the journey like this, what we want to do is we want to write down everything that we know. First of all, these are the things that we know, time and displacement. And then we need to basically identify what other quantities are common, what other quantities are common between these 2 parts of the journey. Now, what's common? There's acceleration that is common. Acceleration for both of them is same. So we can say if acceleration in AB part is A, and this part of acceleration is A, and the next part as well, this is going to be A. But then for the other quantities, final velocity is not common, and also initial velocity is not common. So the other two quantities are not common. That means we would have too many unknowns. If we consider this initial velocity as u and the other we consider that something else, that will be a different value, right? Let's call that 𝗪𝗶𝘃. We have three unknowns. That will be too many unknowns. You would find it very difficult to find those unknowns using these equations. You'll have to solve three simultaneous equations. That becomes too complicated. When you have different parts of the journey like this, we want to make sure that we only have two unknowns. Three unknowns is going to be too many. So breaking the journey like this, AB to BC is not helpful here. Instead of that, we do something like this. We say, let's break it like this. We consider A to B part of the journey and A to C part of the journey, because that will ensure we know the time and displacement for both of them. But then the other two other quantities, one is acceleration and the other is initial velocity, they remain the same for both of them. And that will reduce the number of variables that we've got. We only have two unknowns here, and both of them are common with each other. We can make two equations from them, solve them simultaneously, and find the values of u and a from this. So whenever you have multiple parts of a journey like this, what you want to do is you want to write down all the information that you have already, and then the missing information, try to connect the other quantities, try to find out which quantities are common. So in this case, if you break the journey like this, initial velocity becomes common because that will be the velocity at the point A, and the acceleration was constant throughout. So that's the other common quantity. So we use two separate equations here. S equals ut plus half at squared. In both of them, we get two simultaneous equations, solve them simultaneously, and we get the result. Similarly, if I will do that example later. So this is one case where you have to connect objects like this. We have to connect two equations like this. Okay, let me repeat that. So basically, what we're saying is, if we have multiple parts of the journey like this, you want to first write down all the information that you have for both of those parts. And then for the remaining things, for example, we have u left, we have a left, we have v left. We have u, a, and v left here. We want to write down those quantities that are common between them. They are common between them. Okay. So in this case, final velocities are going to be different, but u and a are common between them. We use those quantities, u and a, because that's going to reduce the number of unknowns that we have. And that's why we break the journey like this as well. We go from A to B and then from A to C, because that makes sure that the initial velocity value is u for both of them, and this is a for both of them, and we avoid having too many unknowns. If we were to use AB and BC, that would be problematic, because even if you say this, that the final velocity of the first part, that is velocity at the point B, that is the same as the initial velocity at for the second part, that's equal to VB. The problem is that's not what we're looking for. We're looking for this initial velocity. How do you find that? That will make it even longer. So you'll first find the value of VB, you'll find the value of A, and then you'll make another equation to find the value of U from that. Right? So that's not going to help. That's going to make it longer. That will be very inefficient. So you want to make two equations such that you get only two unknowns, not more than two unknowns. Otherwise, it becomes fairly lengthy. This is one case where you have to think about this. We will see examples in which sometimes what happens is you've got two separate objects. And they are moving in different directions or in same directions. And we have to consider what happens when they collide, for instance. In that case as well, the quantities that we know, we will write them first. And for the other quantities that we do not know, we will need to find what quantities are common between them. Okay, we'll come to those examples after we discuss free fall. So constant acceleration formulas, they can either be used when the question explicitly says that acceleration is constant. That's one case, because acceleration has to be constant for us to be able to use those equations. But there's some cases for which you need to remember that acceleration is constant. They will not tell you that. For example, you have motion under gravity. Motion under gravity. What's motion under gravity? when weight is the only force acting on an object in the direction of motion, when weight is the only force acting, we call that motion under gravity. There are two types of this. One is free fall. Free fall is when an object is in vertical motion. In vertical motion in the air like this, in vertical motion like this, in this case, the value of acceleration is always going to be 10. It could either be plus 10 or it could be minus 10, one of these two, either plus 10 or minus 10. We'll see how to figure that out. But since it's a constant, we can use constant acceleration formulas in this case when we have free fall. Vertical motion with weight as the only force. No resistance, no nothing. In this case, we call this free fall. Now, what happens when an object is in free fall? So let's say we have this object, we projected it upwards from this point at a speed of 15 meters per second. Okay. Now, when it goes upwards, it will reach some maximum point somewhere, then it'll come down. We need to find, for instance, the maximum height reached by the particle or the time taken until the particle hits the ground. How can you find these two things? Now, when it's projected upwards, we can consider the upwards direction as the positive direction. Now, we will discuss how to take directions in some time as well. But for now, just trust me that we're taking upwards positive, okay? And we will do that throughout the journey. This is very important. Do not break your journey into two parts like this, that you say, while we're going upwards, take this positive, while we're going downwards, take this positive. That will make you do a lot of sign errors in more complicated questions. Plus minus errors will end up getting negative values of time. You're end up getting some positive value where it was supposed to be a negative value, and that will confuse you a lot. Do not change the positive direction mid-journey. Consider the same direction positive throughout the journey. For example, in this case, the particle was projected upwards. What we're doing is we're taking upwards direction as positive. Now, if upwards direction is positive, the particle was projected at 15 meters per second. What happens is at the top, it's going to come to instantaneous rest. At the top, the velocity is going to be 0. Now, while it's going up, its velocity will reduce gradually. So from 15, it'll become 14, 13, 12, 11, 10, and so on. So let's say it becomes 10 here, it becomes 5 here, and eventually it becomes 0 at the maximum point. Now, when it comes back, remember the upwards direction is positive. When it comes back, at this point, the velocity is going to be -5 because it's going downwards now. We were considering upwards direction as positive. So velocity is going to be negative now. At this point, the velocity is going to be -10 meters per second. And then when it hits the ground, it's going to be -15 meters per second, the same velocity from which it was projected. So you see, throughout the journey, what's happening is the velocity is decreasing. It started from a positive value, it started from 15, then went to 10, 5, 0, and then again, it's still decreasing. It's going to -5, -10, -15. Acceleration is rate of change of velocity, not rate of change of speed. So velocity, you can see, is decreasing throughout this journey. Velocity is decreasing. It's going from 15 to 0 and then to -15. Throughout the journey, the value for acceleration here is going to be -10. Throughout the journey, the acceleration value is going to be -10. If you consider upwards direction as positive, remember this acceleration is because of gravitational acceleration. Gravitational acceleration we know is 10 meters per second square. If you're taking upwards direction as positive, gravity acts downwards. That's opposite to the direction that you've taken positive. In this case, the value for A is going to be -10. When you're taking upwards positive, the value for A is going to be -10 here. When you're taking downwards positive, in some cases, we'll see later, when we take downwards positive, in this case, we're not taking downwards positive at all. Throughout the journey, we're taking upwards direction as positive. But when we take downwards positive in some cases, in that case, gravity also acts downwards. In that case, the value of A that we take will be 10 meters per second square. The sign for A here, +10 or -10, that does not depend on which direction the object is moving in. The object can be moving upwards, it can be moving downwards. That does not define whether that does not determine the plus minus sign here. The only thing that determines this plus minus sign is the direction that you've taken positive. If you have taken upwards positive, A is -10. If you've taken downwards positive, A is +10. That's the rule. Okay. So now let's go back to that example. We threw this object upwards. We had to find the maximum height of the particle. Now we know at the maximum height, the velocity is going to be 0. We can say initial velocity was 15. Final velocity was 0. Acceleration is -10y because we're taking upwards positive. And we can find the value of displacement from this. Which equation connects these four things? 2as equals v² minus u². This equation, that gives us the maximum height. If we had to find the time taken until the particle hits the ground, time taken until the particle hits the ground, there are two ways of doing this. One possibility is that you find the time from A to B and then just multiply that by 2. Or you could do it directly as well. You could say, we know that the initial velocity is 15. That's what it was projected at. The final velocity is -15. So you take final velocity is -15. And we know that the value for A is -10. And we also know displacement now, if it reaches back at the same point, the displacement is also 0. So for the whole journey, we know 4 things. We know initial velocity, final velocity, displacement is 0, acceleration is -10. What we can do is we can use any of the equations that have time in them. And that is going to give us the value for t here. That turns out to be 3 directly. You could do it directly like this as well without even breaking it down. You can do this. Why? Because throughout the journey, we know that the value of acceleration is going to be -10. We're not going to change that in the middle. That remains -10 throughout the journey because we're taking upwards direction as positive. Acceleration remains -10 throughout. Yes, so when we take upwards positive, velocity is decreasing throughout. That's why acceleration is -10. When we're taking downwards positive, then while the object is, when we take downwards positive, then the velocity will be increasing throughout, so acceleration will be positive. Okay, but you have to remember this now. If we're taking upwards positive, gravity is acting downwards, opposite directions, A is -10. When they're in the same directions, then A is equal to +10. All right. Okay, now that's one case that in which acceleration is going to be constant. Free fall, vertical motion. Now, another case, it also comes in motion under gravity, and that is when you have a smooth inclined surface. Inclined surface that is smooth, like this. And there's a particle that is moving along the surface. In this case, acceleration is given by 10 sine theta. Now, it comes from Newton's second law of motion, but it helps to just remember this directly. Remember, gravitational acceleration in the vertical direction is 10 meters per second square. This is also a vector. Acceleration is also a vector quantity. So that's like we resolve forces. If we have an object moving along the surface like this, what we can do is we can say, okay, in the downward direction, vertical downward direction, the acceleration was supposed to be 10. What would its value be along the surface? What's the component of 10? Component of 10 in this direction is 10 sine theta. If the angle of inclination is theta, that component is 10 sine theta. That will be the acceleration that we have here. In what case? When it's a smooth inclined surface, that means no friction, and weight is the only force along the surface. Yes, there's normal reaction there, but that's not contributing to motion. That's perpendicular to the direction of motion. So that does not really impact the motion in any way. Along the motion, there is only one force, and that's the weight component. In this case, acceleration is given by 10 sine theta. We know the value directly, that's 10 sine theta. We can use that directly. If you had some other forces, for example, you had friction, there was some other force acting here, maybe of 15 Newton, then you would have to resolve the forces, use Newton's second law of motion to find the value for acceleration. But in a lot of cases, you have this, that weight is the only force, and it's a smooth inclined surface. Acceleration in that case is just given by 10 sine theta directly. Okay, so that's something that you need to keep in mind. That's the other possible case in which acceleration is going to be constant. Motion in the gravity, free fall, or on an inclined surface, when weight is the only force, acceleration in this case is 10 sine theta, and the previous case was 10. Now, how do we decide which direction to take positive and which direction to take negative? So that's, again, a very important thing. Otherwise, you'll do a lot of mistakes. When you have an object that is moving in only one direction, when you have an object moving in only one direction, for example, if you have this object and it's moving towards the right side, and it's only moving towards the right side, you take right side positive. If you have an object that's only moving towards the left side, like this, you take the left side positive. So if it's a single direction motion, object is moving in only one direction, you take that direction as positive. If it's moving upwards only, you take upwards positive. If it's moving downwards only, you take downwards positive. If it's a single direction motion, you take that direction as positive. But if it's like this, that the particle goes to the right and then it comes back as well, then throughout the journey, you take right side positive. Even if it's like this, it's going towards left first and then it's going right. If it's two-way motion, you take right side positive in horizontal direction. If it's vertical motion, two-way motion, upwards and downwards both, you take upwards positive. However, remember, do not change it in the middle. Do not say that while it's moving here, I'll take this positive, then it's moving here, I'll take this positive. No, don't change that. Unless, of course, the journey breaks because of some reason. Sometimes you have collision happening. So if there was a collision happening here at this point, then these are two separate journeys. This is separate and this is separate. In that case, you can take different directions as positive. But if it's the same acceleration throughout, then you would not change the positive direction. You would keep one direction positive and keep that the same throughout the journey. So what's the takeaway from this? Number one, how do you choose positive direction? For each object, first of all, keep one direction positive throughout the journey. Do not change that in the middle of the journey. Keep one direction positive throughout. If the object is moving in only one direction, you take that direction as positive. If it's moving towards right, you take the right positive. If it's moving towards left, you take that positive. Upwards, you take upwards positive. If it's moving downwards, you take downwards positive. If the object changes direction during motion, in that case, what you do is you use what you do in a Cartesian plane normally, XY plane, XY axis, right positive, left negative, up positive, down negative. If it's two-way motion, you do that. Throughout the journey for one object, you will not change the positive direction. If you have multiple objects, for one object, you can take one positive. For the other object, you can take another positive. That's all right. But for each of them, you will keep that direction positive throughout them. You will not change that in the middle. Okay, let's have a look at some examples now. Let's say we got this. We have a particle that's projected vertically upwards from a point O with initial speed 12.5 meters per second. At the same instant, another particle is released from rest at a point 10 meters vertically above O. So you've got this point A that's projected upwards, 12.5 meters per second. You have another particle here that's released from rest at 0 meters per second from rest. Now, what happens is, at some point, the particles meet each other. I'm calling that point X here. And they were initially at a distance of 10 meters from each other. Now, what do we know about each particle? A is moving in the upwards direction, B is moving in the downward direction. So for A, what I do is I'm taking upwards positive. For B, I'm taking downwards positive, right? Because A is moving upwards, B is moving downwards. Now, what's the initial velocity for A? That's 12.5. Acceleration for A, what would that be? That will be negative 10 because upwards is positive, gravity acts downwards. A is negative 10 for this. These are the only two things that we know for A. What about B? B is moving downwards. Initial velocity is 0. Acceleration value, that's positive 10 for this because we're taking downwards direction positive for it. What do we do now? We've got two things known for both of them. Now for the remaining quantities, what's remaining? We've got final velocity, final velocity, displacement, and time. We need to think about how we can connect these two journeys now. Is there anything that's common between them? Both the particles started at the same time instant, and they're colliding with each other. That means from their starting point until when they collide with each other, their times taken are going to be the same. So whatever is the time taken by A, that's going to be the same time taken by B as well. So we can connect them by time. We say the time for both of them is T. Both of them have time T. Can we connect anything else? We have something known about the displacement. What's that? If B is moving SB downwards and A is moving SA upwards, what's their sum supposed to be? The total distance is 10 meters. SA plus SB, that should equal 10. So that's the other variable that we choose to use here. That's displacement. And now we have this equation. We use this equation to find the value of T. That gives us the value for T. And once we have that, we were looking for the height above O at which the particles meet. That's SA. Input that value here, the value for time here, and that will give you the result. That's the height at which the particles meet. So look at the positive and negative direction. For A, we take upwards positive. For B, we take downwards positive. And then we look for the quantities that are common between them. Okay, now let's have a look at this. There's a particle P that's released from rest at a point on a smooth plane. Incline at 30 degrees to the horizontal. Find the speed of P when it travels 0.9 meters. That's really straightforward. But the key thing to note here is we know it's released from rest. Initial velocity is 0. Displacement 0.9 meters. And we don't have any other information. But we know it's a smooth plane. It's a smooth plane and the particle is released from rest. That means weight is the only force that is making the object move down the plane. If weight is the only force, remember, what's the acceleration going to be? Acceleration is 10 sine theta. The angle of inclination of plane is 30 degrees. So we say acceleration, therefore, is going to be 5 meters per second. Since the particle is moving down the plane, we take that direction as positive. It's single direction motion. We take that direction as positive. Gravity also, the weight component also acts in this direction. And that's also the positive direction. So acceleration value here is going to be plus 10 sine theta. And that gives us the acceleration. We can find the final velocity from that. So you see, this is very helpful to remember. Smooth inclined surface, where weight is the only force, remember, acceleration is given by 10 sine theta. Let's take another example here as well. In the first part, they ask you for finding the deceleration. That's straightforward. You have 3 things given. You can find the value of A, and then say the deceleration is 0.5. Acceleration is minus 0.5. The deceleration word already incorporates the negative sign. So when we say deceleration, that will just be 0.5. What about acceleration now? What about the value of alpha now? They're asking you to find the value of this angle. How do you do that? It's a smooth plane and there's no other force acting apart from the weight component. There's no other force acting apart from that. That means acceleration is supposed to be 10 sine theta, right? But since the particle is moving up the plane, we're taking that direction as positive. The weight component is acting in this direction. It will be minus 10 sine theta. We equate minus 10 sine theta with minus 0.5, and that gives us the value for theta. Again, smooth inclined plane with weight as the only force, acceleration is given by 10 sine theta. Let's consider this example. You've got particles P and Q that are projected vertically upward from different points on horizontal ground with velocities of 20 and 25. Now, this is time delay. So these are basically time delay problems. Just write that here. So sometimes we'll see in questions, you have 2 particles and one starts its journey earlier than the other one or later than the other one. How do we deal with problems like these? In the first part here, they're saying find the time for which P's height above the ground is greater than 15 meters. So what does the journey of P look like? It goes up and then comes down. At some point, its height is going to be equal to 15. That's this point. Its height is equal to 15. For what time does the height remain greater than 15 meters? What we can do is, we can say initial velocity is 20, acceleration is minus 10, displacement is 15. Find the value for time when the displacement is equal to 15. And that turns out to be 2 values of time. Time equals 1 and time equals 3. That means while the particle was going upwards, its velocity became 15, first of all, when time was 1, and then it became again 15 when it came down at time equals 3. So what's the time interval for which the velocity was, for which the displacement was greater than 15? That's 2 seconds, 3 minus 2. That's the time duration that we've got. Now that's the relatively easier part. Now the second part says, find the velocities of P and Q at the instant when the particles are at the same height. Now P and Q are projected from different points on the ground. So we've got particle P here, and we've got particle Q here. They were both projected in the upwards direction. Speed for one is 20 meters per second, for the other is 25 meters per second. And they're saying, find the velocities at the instant when the particles are at the same height. Now, what do we know about these two particles? We know their initial velocities. They are 20 and 25 respectively. We know their accelerations. They are -10 and -10. For both of them, we're taking upwards positive, so they are -10. Now, the problem is, what other variables can we connect them by? Displacements. If they're at the same height, their displacements are going to be equal to each other. That's one thing. And we're also given something about time. They are saying Q is projected 0.4 seconds later than P. So Q was projected later. If we consider the time for P as T, the particle that was projected later, we would consider that time as T minus 0.4, not plus 0.4. The particle that starts late, we would consider its time to be less than that of the other particle. Why is that? Think about it. If you have two friends going from one point to another, one starts at 10 p.m. and it reaches the other point at 11 p.m. How much time does it take? 60 minutes. The other starts later. The other starts at 10:15 p.m. The other starts at 10:15 p.m. And he or she reaches the other point at 11 p.m. as well. So they are reaching the same point at the same time instant. But one started late. The one that started late, that took less time. It went at a greater speed to reach that same instant. So the delay was overcome due to more velocity, yes. And the time reduces because of that. So the one that starts late, it takes less time if it is reaching that final point at the same instant. If both of them are reaching at 11 p.m. and one started late, the one who started late, they took less time. That's the idea that we're using here. At some instant, they are at the same height, whatever that instant is. It will be some value of t here. One of them started at t equals 0, the other started at t equals 0.4. So the one that started at 0.4, that takes less time until that time instant. So if we're considering the time for P as t, the time for Q, that will be t minus 0.4. Okay. If we consider this as t, then this would be t plus 0.4. Either of them is going to work. Now, since their displacements are supposed to be equal to each other, we just connect them using an equation like this. That gives us the value for t. Once we have the value for t, we can find the final velocities after that, remembering that the time taken by p was t, and the time taken by q would be t minus 0.4. And that gives us those final velocities that we were looking for. Okay. All right, let's move on. Next thing you have is kinematics graphs. Graphs of displacement time functions and velocity time functions. You'll have to draw these graphs sometimes. You have to interpret these graphs. Okay, you have to sketch these graphs and also interpret these graphs. When you have a displacement time graph, you need to remember, so if you have these three quantities, displacement, velocity, and acceleration. You have these three quantities. As you go from left to right, from displacement to velocity to acceleration, the gradient of the displacement time graph is going to give you velocity, because velocity is rate of change of displacement. Gradient of displacement time graph gives you velocity. Acceleration is rate of change of velocity. So gradient of velocity time graph, that gives you acceleration. And if you go the other way around, if you have a velocity time graph, the area under the graph, that gives you displacement. These are three things that you need to remember. For a displacement time graph, gradient represents velocity. For a velocity time graph, gradient represents acceleration, area under the graph represents displacement. The area under the graph for a displacement time graph, that does not represent anything. Okay, that does not represent anything. Okay, we'll come to that at the end. Okay, at the end when we're done with kinematics and the break, I can come back to that again. Okay. All right, displacement time graph. Displacement time graph. Let's say we've got a displacement time graph here. You need to understand what happens at different points in this journey. You can have a look at this table. At what point and what part of the journey, what is happening from O to A, from A to B, from B to C, from C to D, from D to E. look at these the values of displacement, whether they're going to be increasing, decreasing, or constant. Similarly, for velocity and acceleration, what can we interpret for each of these graphs? You can have a look at this. In this region, displacement is positive, and in this region, displacement is negative, right? That's the quantity that you have in the vertical axis. Gradient of this graph represents velocity. So velocity is constant here because it's a straight line. Straight line have constant gradients. It's zero here because the gradient is zero. The velocity is negative here because the gradient is negative, and it's decreasing as well. It's becoming more steep in the negative direction. And similarly for the other ones, you can see that here. What about acceleration? Acceleration is the rate of change of velocity. So when velocity is constant, acceleration is going to be zero. And it's zero, then also acceleration is zero. When the velocity is decreasing, acceleration is negative, and so on. Okay, have a look at this. We can't go into a lot of detail here, but this is important. From this graph, what you interpret is the direction of motion. If the particle starts from O, from O to A, the object is going in one direction because its displacement is increasing. And then A and B are the same points. At that point, it's at rest. And then from B to C, what's happening is it's coming back to the same point that it started from, because displacement at C becomes zero. So B to C part is when the particle comes back to its initial point, which was this point here. And then okay, then what happens is from C to D, the displacement is becoming negative. What that means is the object is going in the other direction now. It's going towards the left side if the right side is positive. And then it's coming back to the same point again. Okay, so that's what the journey would look like. It's going in one direction first, and then going in the other direction, passing through the starting point, and then coming back to the starting point again. Compare this with a velocity time graph that looks like this. In a velocity time graph, gradient of the graph represents acceleration. So you can see what happens to velocity, displacement, and acceleration in each of these parts here. You can have a look at this. The y-axis represents the velocity value. Gradient represents acceleration, and the area under the graph, area between the graph and x-axis, that represents displacement. Displacement will be positive in this region. It'll start decreasing in this region. It'll be coming back towards zero. I'm sorry, one note is causing some problems here. Okay, so that's the idea. Now, this is important, understanding when the direction is changing in this velocity time graph. So in a velocity time graph, when the velocity is positive, it's positive in all of these regions, right? Because it's above the x-axis. From O to C, the particle is going in one direction. It's going towards right side, if the right side is positive. C is the point at which the direction changes. And that's the point when velocity is equal to zero. And that's important to remember. We will see that later again as well. When you have to figure out the change in direction of motion of an object, we check what happens at v equal to zero. So when v is equal to zero, that is the point when the direction changes, because the particle is going from positive velocity to negative velocity, or from negative to positive. That means the direction is changing. So at c, the direction changes and the particle starts coming back to its starting point, but it does not reach the starting point because this area was more. So it traveled more in the positive direction, and then on the way back, it traveled less. So it does not reach the starting point again. That's what the journey looks like. Okay, so that's the interpretation of this graph. Now, for more details, you can have a look at this table if you want. That tells you what happens in every single part of the journey. Okay. Now we'll have a look at a couple of questions on that. But this is the third part of kinematics, and that is kinematics involving differentiation and integration. We also call this. So the question is, does the object stop at this point C? Not necessarily. It's stopping instantaneously. It's just like when you throw an object in the upwards direction. At the stop point, it comes to instantaneous rest. Its velocity is going from positive to negative, so it comes to instantaneous rest. When the direction changes, there's instantaneous rest at that point. So it's not just stopping altogether. It's coming to instantaneous rest because the velocity is going from positive to negative or from negative to positive. Now, this is the next part of this topic, and that is constant acceleration. That's variable acceleration, kinematics involving differentiation and integration. Whenever you have a function given for displacement or velocity or acceleration, for example, this, do not use constant acceleration formulas. Do not use constant acceleration formulas because they will not work in this case. In most of these cases, those formulas are not going to work because they only work when acceleration is constant. And in most questions that involve these equations, acceleration is not going to be constant. So you don't use those formulas. Now, from those graphs that we discussed, remember the gradient of the displacement line graph that used to give you velocity, gradient of velocity line graph that used to give you acceleration. So how do you find gradient for a curve or for any function? By differentiation. So derivative of displacement is velocity, derivative of velocity is acceleration. If you want to go the other way around, area under the graph, how do you find area under the graph? Generally using integration. If you remember P1 integration, so area under the graph, that corresponds to integration. So when you have to go from acceleration to velocity, you have to integrate. When you go to velocity to displacement, you have to integrate. So if you have any function like this, for example, you've got this displacement function and you want to find velocity, what do you do for that? You differentiate that. If you have to find acceleration from that, again, you differentiate that. You get acceleration function from that. If you have a velocity function, and what you have to do is you have to find the displacement function for that in terms of t. Now, when you integrate, you have to remember you always have a plus c. Whenever you do integration, do not forget plus c. So when you go from velocity to displacement, you have to integrate there. When you integrate, you would also have a plus c. And for finding the value of that c, you'll have some information in the question that you can use. For example, they might give you that at time 0, displacement was 0. Or you might be able to interpret that from the question statement. If the particle is starting from O and its displacement is also measured from the point O, that means initially its displacement was 0. In that case, you could input t equal to 0 and s equal to 0, and the value of c will turn out to be 0. But it's not always going to be 0. Sometimes the value of c could be some other value as well. You always have to find that out. If we have this velocity function, v equals 6t squared minus 12, and we want to find the displacement function from this, we always have a plus c. Whenever we integrate, we always have a plus c there. Okay. And for finding the value of c, we'll have some information given in the question that we can use. The c would represent the displacement of the particle in the very beginning at time equal to 0, only for a function that looks like this. Sometimes you can have functions that have t in the denominator. So you might have, for example, something over t like this. In that case, that's not the same interpretation. It might mean something else. So we can't generalize this, that c will always mean the displacement at the starting point. We'll have to input the value of t and the displacement at that value to figure out what the value of c turns out to be. Okay. All right. Then sometimes they ask you something like this. For example, you have this displacement function and they want you to find the time instant when the particle is at rest. At rest means its velocity is equal to 0. So you find the derivative of displacement function that gives you v equal to 10t minus 2. Put v equal to 0 and that gives you the time value. That's the time instant when the particle is at rest. So at rest means velocity is equal to 0. Okay, now this is important. Let's say we've got this velocity function and they want you to find the displacement of the particle from time equals 3 to time equals 8. So they want you to find the value for displacement from one point to another. This is the velocity function. We want to find displacement from t equals 3 to t equals 8. How do you do that? You integrate the velocity function. When you integrate that, that gives you the displacement function. And then what you can do is you can input limits from 3 to 8, and that will give you the displacement for that. Now, why is that? Because think of it like this. It's a function that's a quadratic function. In this part, it's going to look like this. Area under the graph, area under the velocity time graph, that gives you the displacement. This is the area that we're looking for. How do you find this area? You integrate the function with these limits from 3 to 8. So that's what we're doing. We have the velocity function. We integrate that velocity function. Integration gives us displacement function. And we input these limits from 3 to 8 in that. And that gives us the displacement from time equals 3 to time equals 8. And that turns out to be this value. Now, you have to make sure that you show the step in which you're inputting limits. So when you integrate, you have to show the step, and then you have to input limits and show this step as well, where you're inputting these values of t in this. Once you're inputting 8, and then you're inputting 3 like this. So for displacement value from one point to another, you can use limits like this. Consider this example. You have a particle going from, you have this velocity function, and you want to find this displacement value from time equals 0 to time equals 10. What you do is you integrate velocity, input these limits 0 to 10, and that gives you the displacement from this point to another. I'll answer your question, Dina, in just a few minutes. It's coming. V equals t square minus 11t plus 24. It's the same function that I wrote above there. In the previous example, we had to find the displacement. The displacement turned out to be 23.3 there. Now, if they say find the distance traveled by the particle during the first 10 seconds of its motion, distance traveled during the first 10 seconds, how do you find this? Distance traveled. Remember the difference between distance traveled and distance between 2 points? Distance between 2 points is the same thing as displacement. When they ask you for distance traveled, in that case, now it could be like this, that the particle starts from t equal to 0 and then goes here and then goes here and then goes here. The displacement, it's turning out to be 23.3. That means from the starting point to the end point, this displacement, this is 23.3. But is that the same as distance traveled? No. If the object is changing direction during motion, then the displacement value and the distance traveled, they are going to be different from each other. So how do you find distance traveled? Whenever you have to find distance traveled, you always have to check if the direction of the object is changing at any point. How do you check for change in direction? When the direction changes, velocity is equal to 0. So whenever we have to find distance traveled from one point to another, from one time instant to another, we always do it like this. We say, let's input v equal to 0 first of all. That's the first thing we do. We put v equal to 0. That gives us some time values. These are the time values at which the particle might change its direction. We're getting t equals 3 and t equals 8. That means the particle may change its direction from at time equals 3 and time equals 8. So we cannot find the distance traveled if we directly input limits from 0 to 10 like we did before. That would not work anymore. We would have to break our journey. We have to break our journey into 3 parts. Since the direction is changing at time equals 3 and time equals 8, and we have to find the distance traveled in the first 10 seconds, we break it into 3 parts like this. We say, let's find the distance traveled from 0 to 3, then from 3 to 8, and then from 8 to 10. We find those distance traveled separately. Input limits for each of them separately. The first one gives us 31.5. That's a positive value. This is negative value. This is positive value. So what's that telling us is, initially the particle was moving in the positive direction towards the right side. That's 31.5. Then it moved toward the left side for this much, and then it moved toward the right for 38 over 3 meters. What's the distance traveled? The negative value is just telling you that the particle was moving in the left direction. So for the distance traveled, you would just add their positive values. You'll say 31.5 plus 125 over 6 plus 38 over 3, and that would give you the final result, whatever that turns out to be. That will be the distance traveled. So when you have to find distance traveled from one point to another, when you have equations like these given, always check for change in direction by putting v equal to 0. Okay. So just a summary of what we discussed in the last few examples. You can use limits with integration to find value of displacement from one point to another. So when you have to find value of displacement from one time instant to another time instant, you can use limits like this. If you have to find a function for displacement, for that, you always have to add plus c. Do not use limits there. You should always have a plus c there. Okay. You do not generally use limits for velocity or acceleration. It's possible in some cases, but they will basically tell you the change in velocity from one point to another, the change in acceleration from one point to another. Generally, the questions don't ask you about change in velocity or change in acceleration. So in that case, limits would not have any significance. If you have to find a function for displacement, that means this example, for instance, you have a velocity function. And they want you to find a function for displacement in terms of t, an equation for displacement in terms of t. In this case, when you integrate this, you need a plus c with that as well. Okay, in this case, you need a plus c. That's what it means. When you have to find the value of displacement from one point to another, that from one point to another point, how much distance it's traveling or displacement is traveling, then you can use limits. That's the only case that you would use limits in. Otherwise, you'll always integrate and have a plus c with that. Okay. These integrations are giving us displacement values. These are displacements. That's why it's turning out to be negative. For distance, we do not consider that negative value. We make that positive first, and then we add them up together. Integration gives us displacement, not distance traveled. So that's why we are getting this negative value. Okay. Now, sometimes what happens is we need to find the value of c as well. You'll have some information given in the question to find that value for c. You'll have some information in the question to find that value of c. You'll have to find that value of c. Okay. Now, sometimes what happens is you have multiple equations describing a journey. For example, you have velocity equal to this for time between 0 and 3. You've got velocity equal to this for time greater than 3. Now, when you have multiple equations like this, you need to remember something about this. We have v equal to 5t. That's one equation. We have another equation that's v. That's a constant, where v is a constant. And we have another equation where v is equal to 25 minus t minus 15 whole squared. The first one is valid from 0 to 5. The second is valid from 5 to 15. The third is valid from 15 to 20. Now, the points where you're moving from one equation to the other equation, these are called boundary points. Time equals 5, that's a boundary point because that's when you switch from the first equation to the second equation. Time equals 15, that is also a boundary point because that is when you're switching from the second equation to the third equation. That's also a boundary point. At these boundary points, as you go from one equation to the other equation, remember, the displacement value is always going to remain unchanged. What that means is, if you found the displacement function from this and found the displacement function from this, when you input time equal to 5 in any of them, they should both give you the same displacement value. Velocity is also going to remain unchanged. That means if you input time equals 5 here, the value for velocity at time equals 5 in the second equation is also going to be the same. For example, in this case, the value of v at time equals 5 from the first equation is 25. So that tells us that this constant value that they're talking about here, that is also going to be 25. Velocity at the boundary point is also going to remain unchanged. So you input t equals 5 here or t equals 5 here. Both of them should give you 25. Except in some cases, in some rare cases, where you would have collision. So you have a particle colliding somewhere. in that case, it might be like this, that the particle hits this barrier at some speed, and when it comes back, its velocity instantaneously changes to some other value, for example, -3 meters per second. In that case, it's possible that it instantaneously changes to another value like this, but otherwise, velocity is going to remain unchanged, okay, at the boundary point as well. For acceleration, we cannot say anything. For acceleration, we cannot say anything. Acceleration could be different. It could be the same. For example, in this case, if you find acceleration at time equals 5 from the first equation and the second equation, they are different. But from the second and third equation at time equals 15, they turn out to be the same. So sometimes acceleration is going to be the same. Sometimes it's not going to be the same. Displacement is also displacement is always unchanged. Velocity is also always unchanged, except collision. For acceleration, we can't say anything. It could be anything. For example, let's have a look at this case. A particle starts from rest at the point O, and it travels in a straight line. Its velocity v meters per second at time t seconds is given by v equals at minus 2t square, and we've got another velocity function for time greater than 3. We need to find the distance traveled by p in the first 3 seconds. We can find that. First of all, check for change in direction by putting v equal to 0, then use limits to find that. Then they say find an expression for t for the displacement valid for t greater than 3. Now, how do you think about this? This is the velocity function for time greater than 3, right? This is the velocity function. How do you go to the displacement function from this? You integrate it. When you integrate it, you get something like this. Minus 54 over t plus c. How do you find the value for c in this now? How do you find the value for c? Do we have any point given for this interval? We do not have any point given. But what we can do is, we can say, we have found the value for displacement in the first 3 seconds. That turned out to be 18. So at time 3, the value for displacement was 18. There was no change in direction in this case in the first 3 seconds. So displacement and distance are equal to each other. At time equal to 3, displacement was 18. That point can be used here as well to find the value for c. We can say, since at time 3, displacement was 18, it is going to remain unchanged at time equals 3 for this equation as well. We can use that value from the first equation in this equation to find that value for c. And the displacement function turns out to be this. So at the boundary points at time equals 3 here, the velocity values from both functions, they're going to be the same. If there's no collision, and the displacement value, they're also going to be the same. Acceleration may be different. It may not be different. That depends. That can vary. Then it says value of v when the displacement of p from O is 27. Now that's straightforward, relatively straightforward. It says the value of v, that's what you want to find out when the displacement from O is 27 meters. You find the displacement function. We know that the displacement in the first part of the journey was only 18. So it's definitely not happening in the first part of the journey. In the first 3 seconds, the maximum displacement was 18. We found that in the first part. So 27 is going to be after that. We've already found the displacement function in the previous part. We can put displacement equal to 27 here, find the value for t from that, and put that in the velocity function. You'll get the corresponding value for velocity as well. But the important point was this. At the boundary points, how the displacement and velocity, they remain unchanged, because you can use that to find the value for c sometimes. No, the question says it's greater than 3. So this velocity function is only valid from when time is greater than 3. Greater than 3 basically means 3.0000001, right? Any value that's even slightly greater than 3, this function will become valid at that point. Okay, it's coming very soon. Not very soon, but maybe 10-15 minutes. Okay, now it's just about some examples that I want to show you, and then we complete kinematics. maybe I can skip some of them as well. You can have a look at them in your own time. I'll just show them to make it slightly quicker. A particle starts from O and moves in a straight line like this. You've got this velocity function. Verify that the particle returns to O when t equals 2. Returns to a point. What does that mean? The displacement is going to be 0. So whenever they say a particle or an object returns to its starting point, that means displacement should be equal to 0. So how do you do that? You find the displacement value when time is equal to displacement value from 0 to 2 and see what that turns out to be. If that's 0, that means the particle returns to the starting point. Okay. The second part is you can have a look at that working. They're saying look at this question. You can take a snapshot if you want, or look at the notes if you want. But the first part was what I was interested in this part, in this question. The other, you can see the working for that. It's not that difficult. This is the next part. Let's have a look at this one. Okay. Now, in this example, yeah. So sometimes they will say, find the maximum velocity of something. Maximum velocity of something. Now, you have the velocity function given. You've got the velocity function given for that part in, that they're talking about. How do you find maximum value of anything? How do you find maximum value of anything? Of any function? You find the derivative, but that equal to 0. You have the velocity function here. You want to find the maximum value for velocity. How would you do that? You would say, this is the velocity function, find the derivative of that, put that derivative equal to 0. That will give you a value for t. That's the turning point. That's the maximum point. Put that value of t back in the velocity function, and that will give you the corresponding velocity value. Right? So that's the maximum point that we were looking for. So sometimes when they ask you for maximum value of something or minimum value of something, you can use differentiation like this, put that equal to 0. Now the rest of this, you can have a look at this in your own time. I'll go through this slowly. Okay. All right. Now, look at what the question statement says. Given that there are no instantaneous changes in velocity, find P and Q. What does that mean? No instantaneous changes in velocity. What that means is, you see the first velocity function that's valid from 0 to 6, the second velocity function that's valid from 6 to 14. At time 6, that's the boundary point, the velocity does not instantaneously change to another value. Whatever is the velocity value from the first function, it will be the same velocity value that you get from the second function when time is equal to 6. So using that now, you can find the values of P and Q. What information are we given? We're given the acceleration of P is 0 when time is equal to 2. That's one piece of information that you can use here. Find the acceleration function from the first one, because that is valid when time is 2. So that's what I've done here. Found the acceleration function. Put time equals to and equal to 0 in that, and that gave us an equation in terms of P and Q. That turns out to be this: Q equals 4 times P. And then we know that at time equal to 6, the velocity from both of these functions is going to be equal to each other. So what we do is we put time equal to 6 in both of these functions and equate them. That gives us another equation, and that's going to give us the values of P and Q. All right. Now in the next part, they say, sketch the velocity time graph. Now we've got the two parts of the velocity time function here. One is a quadratic function. You draw it like you draw any quadratic function. How do you draw quadratic functions? You need two sets of points for them: turning points and intersects. You always have to find turning point while sketching quadratic graphs. The second part of the function was a straight line, 63 minus 4.5t. So you've got a quadratic function and you've got a straight line function. Now, how do you draw them? You have to find the values of velocity at extreme points. First of all, this is valid from 0 to 6. How would you draw that? You would find the value for velocity at time equals 0. At time 0, velocity turns out to be 0. Then you find the value of velocity at time equals 6. That's the other extreme point. And that turns out to be 36. That's this extreme point. Then you find the x-intercepts. One is 0. Can you find the other one? Just factorize this. Put v equal to 0. And that gives you time equals 0 and time equals 4. These are the two x-intercepts that you have for this graph. And the turning point, therefore, is going to be in the middle of them. It's a symmetric graph. Whatever are the x-intercepts, the turning point is going to be exactly in the middle of them. So this is the turning point. So the graph looks like this. And then the second part is just a straight line. You can draw a straight line like that. That's what the graph looks like. So sometimes it can be weird like this. It goes below the x-axis like this, and then it comes back. If you just take extreme points like this point and this point, you might mistakenly think that the graph looks like this. Don't do that. You have to consider the turning point as well. So if you just consider this point and this point, that will make you think that it's going to be like this. You always find the turning point as well. You can find it using the standard method as well, minus b over 2a. Yes, you can do that, minus b over 2a, or differentiate, put that equal to 0. Any of them will work. Okay, but in this case, since we had already found the x-intercepts, turning point is going to be exactly in the middle of the x-intercepts for a quadratic function because it's a symmetric graph. So you can do it like that as well. Total distance traveled by the particle during the 14 seconds. You can see direction is changing at the point 4. So you have to break your journey at the point 4, right? That's important because the direction is changing. So what you would do would be the first function, you would find the displacement, you would input limits in this from time equals 0 to 4 first, and then from 4 to 6. And that will give you the distance traveled during the first 6 seconds of motion. And then for 6 to 14, you use the other equation, or you can just use the area of the triangle here as well, area in the graph. That will be actually easier. Add that number here, and that will give the total distance traveled. You find the distance traveled from 0 to 4, 4 to 6, make them positive, add them up together, 32 plus 32, plus 144, that's the area of that triangle, and that gives you 208, and that's the total distance traveled. So sometimes you have to sketch graphs like this yourself as well. Okay, now, in very rare cases, this can happen as well, that one part of a journey is dealt with using constant acceleration formulas. And then for the other part of the journey, you have to use these equations. For example, you've got this particle P that's held at rest. It falls freely under gravity. That means the value of acceleration is negative 10 or plus 10, depending on the direction that you're taking positive. In this case, we're taking downwards positive, so it's plus 10. Until it reaches the point A, which is 1.25 meters below O, the starting point. Find the speed of P and the time taken. That's just the use of constant acceleration formula that's going downwards. And we know the initial velocity, we know the displacement, we know the acceleration. We can find the final velocity and the time. But then it says the particle continues to fall. But now its downward acceleration is given by 10 minus 0.3 times t. So after this point, we have an acceleration function like this. It's no longer constant now. Acceleration is in terms of t. So in one part of the journey, acceleration was constant, that was 10. In the next part of the journey, you have this acceleration function that's not constant anymore. We need to find the total distance P has fallen 3 seconds after being released from O. Now, notice after being released from O. So 0.5 seconds have already passed. 0.5 seconds have already passed before. So we need to figure out the further distance traveled in the next 2.5 seconds. What would that be? You know what happens from O to A. The initial part of the journey, you knew the initial velocity for that. You knew the final velocity. You find the displacement, you find the final velocity. You got all of that information. And then for the next part of the journey, when the particle is going at an acceleration of this, you have to find the distance traveled in this part of the journey. How do you do that? In order to go from acceleration to displacement, you have to integrate twice. You integrate acceleration once, and that gives you this velocity function. But whenever you integrate, you have a plus c there. Whenever you integrate, you have a plus c there. Okay, we're almost done. We're almost done. And then we'll have a longer break. Okay, so I'm just going to do a quick vote. How many of you have an exam on Monday? How many of you have an exam on Monday? Raise your hand if you have an exam on Monday, quickly. What are the exams on Monday? What exam do we have on Monday? EM? But that's what people give in AS generally. So, okay, so some AS people might have that. All right. And that's it. Okay. So we are going to continue after the break. We're going to continue. But if you get too tired, can we do early morning tomorrow? Do you think that will work? Early morning, I'm not saying after Fajr. I mean, before noon. Do you think that might help in case it's becoming difficult to digest now? AS English and EM. Okay. All right. So how early can we do tomorrow? So maybe like 10 to 11:30, something like this, 10 to 11:30, 7 a.m. I'm not sure anyone is going to be up at that time. Will that work for everyone? Sure. Because I'm getting messages now that you're getting zoned out. Multiple people saying that. I'm fine with either. I am used to teaching long classes. So I'm fresh. I'm not fresh, but I would like to believe I am fresh. Okay, so we'll have a break and we'll try to do as much as we can. So even if we have to do it in the morning, we could have a very short session, maybe an hour. Then try to do as much as we can right now, and then we can maybe uh, come have a short session tomorrow if needed. Around 30 minutes. Around 30 minutes. But it's not right now. It's not right now. It's not right now. In about 5 minutes. So what happens is the particle goes down. So we have this velocity function. It has a plus c. How do you find the value of the c? We had the final velocity from this part of the journey. We had the final velocity from this part of the journey. We can use that here. We can say at time 0, the velocity is 5. Now, remember, the time for this acceleration function is starting after passing A. So at the point A, it's time 0 for this equation. So at time 0, we know the value for velocity is equal to 5. We can input that here to find the value of the c. Once we've got this value of c, now we've got the velocity function. We integrate it again to get the displacement function, and we input limits from 0 to 2.5 there to get the distance traveled in the second part of the journey, and then we add those two distances together, and that gives us the total distance. So the idea is sometimes you can have something like this as well, that in one part of the journey, they ask you to use constant acceleration formulas, and then in the second part of the journey, they want you to use an equation and use differentiation integration to figure that out. So that's also something that happens sometimes. Okay. I'll do is I will skip this example, move on to this one. Okay. A particle P moves in a straight line, and we've got the velocity function here. And it's defined in 3 different parts like this. 0 to 4, 4 to 14, 14 to 20 like this. We have to find the value of k first of all. How can we do that? Again, use the boundary points. At time equal to 4, for instance, whatever is the velocity value that you get from the first equation, that will be the same value that you get that you should get at time equals 4 from the other equation. So whatever is the velocity at time equals 4, that is 40 here, that should be the value of k in the second part of the journey. Then they ask you to sketch this velocity time graph. Again, it's a quadratic function, so you have to think about the turning points, about the intercepts, and then draw that. The second part and the third part, they are just straight lines. You draw them like this. Now the third part, that's what I wanted to focus on this question. Find the set of values of t for which the acceleration of p is positive. Find the set of values of t for which the acceleration of p is positive. What does that mean? It's a velocity time graph. In a velocity time graph, acceleration is given by the gradient of the graph. So in what part of this is gradient positive? It's this shaded part in which the gradient is positive. The turning point was at 1. Gradient is positive from 1 to 4. So we say acceleration is positive from 1 to 4. That's the region in which acceleration is positive, from 1 to 4. Okay. You could also do that. You could find the derivative of velocity, put that greater than 0. Put acceleration greater than 0. Would you get something from that? This is velocity. This is 5t squared. The velocity function is this. Yeah, v equals 5t squared minus 10t. If you find the derivative of that, acceleration turns out to be 10t minus 10. When is acceleration greater than 0? From this, you just get t greater than 1. So for this quadratic function, yes, it's greater than 1. But there's an upper limit as well, because this function is only valid. This function is only valid up to time equals 4. So for that reason, we would say that it's positive for time between 1 and 4 like this. That's the region. In which it will work. No, in this case, so the question is, do we always have to visualize it like this? In this case, since we had the graph given, it was easier to do it from the graph itself. But if we did not have the graph given, then you would do that. You would say, find the derivative of v, find acceleration, put that greater than 0. That's what you would use if you did not have the graph given. Okay. Find the total distance traveled by p. We have discussed that before. So you break the journey into multiple parts, 0 to 2 separately, because that's where the direction is changing at time equals 2. And then from 2 to 4, because that's what this part of the function is valid for, until 4. And then from 4 to 14, we have a horizontal line. And then 14 to 20, you've got that inclined line, downward sloping line. Then it says, the man fires and... okay, so there's a man who fires a distress signal. So I've just taken one part of a question here. Vertically upwards from sea level. The signal is above the sea level on the top of the cliff, and the cliff here is at a height of 40 meters. So we have a cliff that has a height of 40 meters. Let me go back to that. We have a cliff that has a height of 40 meters. We need to find the speed of projection of the signal. Okay, now how do you find the speed of projection? We have a cliff that is 40 meters high, and we are given that this time interval, for which the particle is above the level of the cliff. This part. This time interval is under root 17. How do you find the speed of projection, the speed at which the particle was projected in the upwards direction? This is one way of doing this. You say, let's break this journey. You got one part of the journey from A to B, and then from B to M. M is the maximum point. It often helps to mark those points in your diagram, on your diagram, because you can then refer to those points easily in your working. So B to M is one part of the journey. A to B is another part of the journey. So what we want to do is we want to find the time taken from B to M. And then we can just multiply that by 2. That should equal under root 17. So I'm doing it like this. I'm saying, okay, what do we know about B to M part of the journey? We know the final velocity, that's going to be 0 at the maximum point. We know the time taken for that. If the total time was under root 17, the time taken for this half journey, that is under root 17 over 2. Half of that. What about acceleration? That's negative 10. Now, using this, what we can do is we can find the initial velocity of the particle. That means the velocity of the particle at the point B. And that turns out to be 5 under root 17. Now, this can be used as the final velocity for this part of the journey. For A to B part of the journey, the velocity at the point B, that turns out to be 5 under root 17 meters per second. Now, that will be the final velocity for A to B part of the journey. Now, for A to B part, we know displacement is 40, acceleration is minus 10, final velocity is 5 under root 17. Find the value of initial velocity. That will be the velocity at the point A. That's what we were looking for. That turns out to be 35 meters per second. So you often have to break your journey into multiple parts like this, where final velocity of one part becomes the initial velocity of another part. In this case, initial velocity of one part becomes the final velocity of the other part. Okay. One last example, and then one last concept after that. There's a particle P that travels in the positive direction along a straight line with constant acceleration. So now in the question, they've given us that it's constant acceleration. P travels a distance of 52 meters during the second second. During the second second, what does that mean? Time equals 1 to time equals 2. And then it travels a distance of 64 meters during the 4 seconds. That means from time equals 3 to time equals 4. Find the initial speed and the acceleration of the point of the particle P. How do you find that? You can say, if it's constant acceleration, then we can write down the displacement of the particle in terms of t like this. S equals ut plus half at square. We can use that function. Let's write down the displacement function in terms of t. We know that from time equals 1 to time equals 2, the displacement is 52 meters. So in this displacement function, we can input limits from 0 to from 1 to 2 and say that this should result in 52. Simplify that and you get an equation in terms of u and a that looks like this. Similarly, from 3 to 4 seconds, the displacement covered is 64. So again, now you input limits from 3 to 4. You get another equation from that in terms of u and a. Solve them simultaneously and you get the values of u and a from that. Okay, so this is the question. This is the type of question that they've given like 2-3 times in the recent papers as well. They tell you the distance traveled during a particular second. So during the second means from time equals 1 to time equals 2. During the 4th second means from t equals 3 to t equals 4. So you can use limits like this after finding the displacement function. One last concept that you will use in the more difficult questions. So we have not talked about the kinematics and momentum questions, right? We'll talk about them when we talk about momentum. Those are, I think, the most difficult types of questions in mechanics, where they have kinematics and momentum, both of them. In many of those questions, we have this concept that you'll have to use relative speed. Relative speed. Now, let me explain what that means. Let's say you've got two particles. This is A, this is B. And they are at a distance of 40 meters from each other. A is moving towards the right side at 7 meters per second. B is moving towards the left side at 3 meters per second. in how much time at what time value are they going to collide with each other? At what time value are they going to collide with each other? That's what you want to figure out. How can you find that? Think about it. Every second, A is moving 7 meters to the right, and every second B is moving 3 meters to the left. So in 1 second, they are getting closer by 10 meters. They're getting closer by 10 meters. We can say the relative speed for them is 10 meters per second. That every second they're covering a distance of 10 meters. So relative speed can be thought of as the speed at which the distance between two objects is covered. Now, the distance between these two objects was 40 meters. If A moves by 7 meters per second to the right and B moves by 3 meters per second to the left, how much distance are they covering in every second? They're getting closer to each other by 10 meters. So we'll say the relative speed is 10 meters per second. Okay. So how do you find time until they collide? 40 is the distance. Relative speed is 10. That turns out to be 4 seconds. So when particles are moving in opposite directions, that means towards each other, the relative speed is going to be the sum of their individual speeds. We add them up together like this. The other possibility is we've got these two particles A and B, again, the same distance between them. Let's say A is moving towards right at 18 meters per second, B is moving towards right at 13 meters per second, and the distance is this. How much are they getting closer to each other in every second? A is moving in 1 second 18 meters to the right, B is moving at 13 meters to the right. So distance between them is going to reduce by 5 meters because A is traveling 5 meters more than B. So distance is going to reduce by 5 meters. Okay. So what's the relative speed then? 18 minus 13, and that turns out to be 5 meters per second. The distance between them reduces by 5 meters per second. So that's your relative speed. How much time would they take until this collision? 40 over 5, that's 8 seconds. So when they are moving in the same direction, then the relative speed is going to be the difference of their individual speeds. 18 minus 13, that's the relative speed. A is approaching B at a speed of 5 meters per second. So the distance will be covered in 40 over 5, that's 8 seconds. Does that make sense? Any issues with this? Now let me know if there are any questions. If I missed some questions in the middle, let me know about them.
ठीक सर एक क्वेश्चन था कि जो न्यूटन सेकंड लॉ ऑफ मोशन है उसमें RF इज इक्वल टू एम ए, उधर भी एक्सेलरेशन जो होती है वो कांस्टेंट हम अज्यूम करते हैं जब हम निकालते हैं खुद या दी जाती है.
F equals ma में we don't say anything about acceleration being constant or not. F equals ma is used for at a particular point. एक point पे तो acceleration कुछ भी हो सकती है. Constant होती है if a particle is going from one point to another. Now during this journey, acceleration remains constant at a particular value. But F equals ma, that is generally used at a particular point. So let's say the particle is at this point. At this point, we say, okay, these are the forward forces, these are the backward forces. What's the acceleration at that particular point? So this only gives us acceleration at a particular point. So that can be used whether it's constant acceleration or variable acceleration.
और सर एक और क्वेश्चन
It works
था,
for both of them.
अगर वो सारी फोर्सेस इक्वल हों तो उसमें एक्सेलरेशन जीरो होगी या कांस्टेंट?
कांस्टेंट होगी. सारी फोर्सेस इक्वल होती हैं तो एक्सेलरेशन कांस्टेंट होती है. Let me actually add that here as well. That's an important reminder. We generally discuss that in Newton's second law of motion later on, because that's where its questions come. But let me just add that to the notes here as well. Newton's second law of motion. Where would I have that? So Okay, so one case was when the question tells you that when the question tells you that acceleration is constant. The other possibility is it's motion under gravity. That means it's free fall, or it's an inclined surface with the weight as the only force and the surface is smooth. Another possible case is whenever all the forces acting on an object are constant, in that case is where acceleration is constant. So if you're sure in a particular case that all the forces acting on an object are constant, that would mean that the resultant force is constant. If the resultant force is constant, that would mean acceleration is also going to be constant, right? Because mass is always constant, mass does not change. So if resultant force is constant, that means acceleration is also constant. So sometimes you can infer this from the question statement and then use constant acceleration formulas. If any force is changing, then acceleration is not constant, then you cannot use that. Okay.